Hi guys, Dr. B here. This is a partial key video explaining how to do problems 4 and 5 from your homework. A 8.15 gram sample of hydrogen peroxide decomposes to form water and oxygen. The temperature and pressures conditions in the lab were 21.2 degrees Celsius and 761.4 torr. The oxygen gas is collected over a sample of water at 21.2 degrees Celsius. The vapor pressure is 18.9 torr. When the water level inside and outside of the tub is equal, the volume of the gas is recorded as 176.23 milliliters. So first we got to write out and balance the equation for the decomposition reaction. So we know that it is H2O2, and it's saying that it's decomposing to form water, H2O, and oxygen. That is a diatomic element. Now you need a balance. There's 3 oxygens on the right, 2 on the left, so I'll put a 2 up here in the front. That makes it 4. I can put this 2 over here in front of the H. Now there's 4 H's and now 4 O's. What is the partial pressure of just the oxygen gas? So you have the pressure of the reaction, the conditions were 761.4 torr. It is collected at the oxygen gas is, the oxygen gas, the vapor pressure of the water is 18.9 torr, so the rest is the vapor pressure of the oxygen. So 742.5 torr. Assuming no deviation for ideality, how many moles of gas were produced? So that, luckily for us, that's just PV equals nRT. We want the moles, so divide both sides by RT. The pressure, so because the pressure is in torr, we need to put it in atmospheres. Let me get my calculator quick. Based on the gas law constants we have in our list, we're going to have to use this one I'm going to give you, or the one that we know of, I'm sorry. So your pressure, 742.5 divided by 760, convert it to ATMs. So keep kind of running out of space. So pressure equals 742.5 torr divided by 760. That would equal approximately 0.9769 something ATM. So 0.97. Oh, how many sig figs again? There's too many sig figs to worry about. Let's do 3, I guess. Too many sig fig rules to think about. So that's ATM times my volume. So this is actually milliliters, so it needs to be in liters for our constant. So 3 to the left, 1, 2, 3, times 0. Divided by R, 0.08206, times your temperature, 21.2 plus 273, 294.2 Kelvin. But I think if it's a 0.15 that they have on your thing, so then 294.4. This will give me my moles, so 0.97 times 0.17623 divided by On your calculators, you should have gotten, sweet. Let's see. Oh wait, so with this sig figs here, yeah, we should have had 4 sig figs. So let me do 6. Is this still 7? Oh, yeah, can't find whatever. So 4 sig figs. So then it would be 0.007127 moles of O2. So we'll try to keep that in mind. You have that on your paper, hopefully. 0.007127 moles of O2. What is the mass of hydrogen peroxide that reacted? So we are going, this is an easy one. You're going to take your moles of O2 and convert that over to grams of hydrogen peroxide. That's good. That's easy. 1 mole of O2, 2 moles of H2O2. I don't have a lot of space for this for some reason. I don't know why. 1 mole of H2O2 on the bottom. And then on the top, this is 1.008 times 2 plus 16 times 2. I have 34.016 grams of H2O2 times 2 times 0.001727. You should have gotten, with your still sig figs, 0.4849 grams of H2O2. What is the percent by mass of the hydrogen peroxide from the original sample? So they actually gave us a sample for the whole reaction we're going to use. So you're going to take your 0.4849 grams divided by, in the problem it's 8.15 grams times 100 will give me my percent. My shoulder hurts. Sorry. So you end up with 5.95%. It'll take a while. Okay, so a 25.0 milliliter sample of 0.25 potassium carbonate solution is added to 30 mLs of 0.4 molar barium nitrate solution. What is the concentration of the excess metal ion after the precipitation is complete? So we got to figure out what is our limiting reactant, unfortunately. So I'm going to convert both of my reactants to barium carbonate, because barium carbonate is my precipitate. So these are all in milliliters. So a quick way just to do this, so 25.0 milliliters over 1, so that in 1,000 milliliters, actually 1,000 milliliters, so you can even say in 1 liter, it's the molarity, so it's also 1,000 milliliters. So that makes it even shorter. So this is going to be my potassium carbonate. So I'm going to convert this over from, we need to first get the reaction, my bad. So K2CO3 plus barium nitrate. It will produce, looks like potassium nitrate and barium carbonate. That is my precipitate. Because the potassium and the nitrate, that's definitely going into solution. To make sure it's balanced, put 2 in front of the KNO3, call it a day. Luckily for us, 1 mole of barium carbonate equals 1 mole of K2CO3. We do our math, we end up with approximately 0.0625 moles. Let's do the same thing with our other reactant. Which is barium nitrate. Okay, so then in 1 mole of barium nitrate, it is 1 mole of barium carbonate. You end up with 0.012 moles. So what you need to know and recognize is that your limiting reactant is potassium carbonate because it gives you the least amount of moles. So you're going to take your moles of 0.00625 moles of barium carbonate, because it wants just the excess metal ion. So in 1 mole of BaCO3, you have 1 mole of barium ion. Okay, good luck. The idea is that you are converting, obviously, but like you're converting the units, so it's important to recognize what the units are now. So now our unit is 0.00625 moles of Ba2 plus. So this is how much moles of barium 2 plus will be used by the precipitate. So I need to erase this because I need actual spaces. So hold on 1 second. So I'm going to get rid of the top ones for now. So I'm going to change color so we know that we are starting this continuing after I erase that. I'll change to a green. So to find how much there was initially, you're going to take your 30 mLs again of barium nitrate, get the molarity, okay, I'm done. So, this will be 0.012 moles of barium initially, because again, it's in 1 mole of barium nitrate, there's 1 mole of barium ion. So you're going to take these two numbers and subtract them. You end up with 0.00575 moles remaining. And I know sig fig rules and all that, but for now, so we can just see that's how many moles we have remaining. So let me erase this on the bottom. Oops, what the heck? Okay. Okay. So in this total solution, we got to find the concentration. So luckily we have these moles of barium ion. So we want the total solution. To do that, and we want, moles per liter and everything, blah, blah, blah. So let's just do 25 plus 30. So we have our, so we have 55.0 milliliters. Make that into liters, 3 to the left, right? So 0.0550 liters of solution. Divide the two, you end up with 0.105 molar solution of molar concentration of barium ion. That was a lot. So think about if we're following sig fig rules, it would be like 0.111 or something, 0.11 or something like that. Anyway, that was a lot. So please look at this if you struggled with the last two problems. Let me know if you have any questions. Okay, thanks. Bye.